Hello, my friends. How are you? Can you hear me?
Hi, good morning. I'm fine, thank you. Yeah, I can hear you perfectly.
Hi. Great. So welcome to our international school. My name is Rustam. Uh, I am PhD student of engine production technologies, and I am going to talk about 3D printing in aerospace technologies. First of all, I would like to thank you and say that we are very happy that you want to participate in our international school. And I hope my lesson you'll find something interesting. So before start, I would like to ask you, what do you know about space technologies? And what you know about 3D printing?
In my university where I studied the bachelor, we had a little 3D printer, and that worked with a little plastic kind of filament, like a little tube that goes into a pin, and there it's heated, and then additively kind of layer by layer a part is kind of formed. And as far as I've heard, you can also use nowadays different materials to make even harder parts, not only like these softer plastics. But yeah, that's about it.
And what about space technologies, just except rockets, maybe aircrafts?
You mean in the context of 3D printing as well? Because I think, I think nowadays some companies also make lots of, even rocket companies make some parts with 3D printing. I think I've heard like SpaceX and these people make like engine parts also with 3D printers nowadays, and it's getting very popular, I guess.
Great. And what do you know about 3D printing in a space application? Just have you heard something new nowadays? What they are making using this kind of technologies? Maybe some parts, maybe some I don't know, aircraft parts for the engines, for the wings, and for the planes.
Yeah, I don't actually know any specifics about it. I only heard that they make parts now with 3D printing. I don't know actually. Yeah.
I see, I got. Okay, let's start. Today I'm going to talk about 3D printing in space application. If you want to know deeply about the exactly additive manufacturing or 3D printing, I will show you another presentation later. So 3D printing in, or we can call it additive manufacturing in aerospace industry. Additive manufacturing or 3D printing, it's known as joining material and make an object from 3D model or 3D data. Usually we are using layer by layer technology. In material, we can use plastic, we can use metal, maybe some compounds to create our data from 3D model that were created in computer programs. So in aerospace industry, we can create lightweight structure, for example, for the wings of the planes, some generative design, some topological optimization. Later we will talk about it. Some extreme temperature gradient. Again, this 3D modeling can help us to create very complex details for turbojet engine, for example, blade, some parts of combustion chamber, etc. Also, some parts which consist complex geometries like blade, turbo blade, another usage of it in rocket industry or rocket engines. For example, assemble with too many components. For example, small nozzles for the rocket engine. Additive manufacturing provides us freedom in component design and fabricate very complex details, very complex components or 3D geometry. And the following this complexity can be easily achieved. Some features, for example, wearing thick, deep channels and cuts using this technology. Some geometry. In geometry, we can create different types of geometries because our 3D model can be divided in the small layers. And layer by layer, we can create any complex form. Parts consolidation. Traditional manufacturing parts requires joining together. Now can be integrated into a single printed part. For example, if we want to create nozzle for combustion chamber, can be created by traditional technologies. And this detail consists of 3 or more parts. In 3D printing, we can join these parts and create as a complex whole detail using this technology. Fabrication steps consolidation. It can be fabricated nesting parts that requires assembly in multiple steps, can be printed as simulation. What does it mean? We have special programs to simulate the process of 3D printing. Later, maybe I will show you this kind of programs. For example, let's take one big company as General Electric. Maybe you heard about it. They're creating one of the best jet engines for aircraft, for the planes, as A320 or Boeing 737, and all the planes using General Electric engines. These engines consist some parts that were created or fabricated by 3D printing. For example, more than 30,000 parts since 2015. They're using this 3D technology to create these nozzles shown on the screen. The number of parts in a single fuel nozzle tip was reduced from 20 pieces to 1. It means they are joined, as I told before, some complex parts as a one part and printed it in one operation. The nozzle tip's weight was cut by about 25%. It means these engines became lighter and more productive. Also, it became serviceable time of the component increased by the 5 times. It means if we want to change the part inside this engine, it will be easily because we can just take out the broken one parts, print it again, and add to this engine using this again 3D printing. In rocket industry, maybe you heard this kind of film like Firefly rockets. They're using this technology to create combustion chambers for the rocket jet engine. And as you told Philip before, again, this SpaceX company using this kind of technology. If I remember, in 2019, they created a combustion chamber for the Crew Dragon spacecraft, and they tested last year. 2019, I think, or last year, I don't remember exactly. They tested, and in April last year, they ascended the crew to the International Space Station. As you see, this company is progressive. SpaceX, again, everybody talking about that. Elon Musk, yes, he's professional, he's businessman. And as you see, he also found something interesting in 3D printing and using this kind of technology in his company, because it's kind of advanced technology and useful for this kind of industry, for the rocket engines, for example. Let's talk briefly talk about the liquid rocket engine and which kind of compounds it consists. As you see on the screen, it consists of some pumping um, mechanism, controllers, starting burner, injector. Here it's shown, combustion chamber, very complex cooling system that sends the fuel around all this combustion chamber. It's using two functions. It cools this combustion chamber during the burning and send the fuel through the nozzles. And again, nozzle design. This is a simply complex form of the rocket engine, but nowadays there became more complex because many kind of new details added to that rocket engine. In SpaceX, for example, it's totally different. Rocket engine that were created 30 years ago. Nowadays, they are more complex. Here, the cooling the system for these jet engines, it takes about 3,000 degrees Celsius during the process of burning. That's why we need very strong and innovative materials to create this combustion chamber. Here you see the example for cooling channels that they are used for these rocket engines. Heat exchanger. Fuel comes from the pump. It pumps through all this nozzle and all this combustion chamber, and it's work as a cooler for that engine. Some oxidized products are added through the nozzles for the injection, and combustion chamber it occurs inside this chamber. It starts from 1000 degree and increase here to 3000. As you see in traditional variants, in traditional technologies first, it was using molding or casting to make this complex nozzle, or sealing and milling machines, also CNC machines were used to cut out this nozzle from the complex metal. And nowadays, some companies using the 3D printing to create this kind of complex form, and it's very useful. But this traditional technology comes from 1962, as you see in the screen, how the traditional process was occurred. The people manually was putting these cooling channels around this nozzle. It took time and it was very difficult to put even all these burners, all these cooling channels around this nozzle. But was useful at that time, about 30 years ago. Now technology doesn't stop; it improves itself, and now we have 3D printing. Here you see some injectors for the rocket engine. At the right side of the screen, you see our Russian-made rocket engine with a combustion chamber, and its name is RD-180, rocket engine 188 in translation from Russian. Injectors use high pressure gradient, corrosive fuel, and oxidizers. Precision holes. It consists of hundreds of individual components, and the materials it's anti-erosion. You see here very tiny complex injectors on the top of the combustion chamber that used. Here from the left side you see traditional technology. It was made by CNC machines. Again, it looks advanced for today's technology. Even I am not saying that all the manufacturing they're transferred to the 3D printing. No, they're still using CNC machines because they're useful to make useful roughness of the surface of each component. That's why still people here 3D printed fuel injectors. From 2015, NASA agency used this technology as firstly an experiment. Let's see what it has some advantages or disadvantages. About disadvantages, I will talk later. Since 2010, different projects has been developed using additive manufacturing. Here you see an examples that was made by 3D printing. So about disadvantages. First, I would like to ask you, what do you think about the disadvantages of 3D printing?
I mean, maybe you cannot use any material, right? Just some materials
One of it, yes.
can be used for 3D printing.
And other disadvantages? You remember I was talking about roughness of the surface. Another one. So what else?
It takes a lot of time to print bigger things.
Somehow, but it's more advantage than disadvantage. I'll talk later. The size of the print, yes, it's totally different, but we can use direct metal deposition. Later, I'll talk about it. It's not layer by layer creation. Detail, it's using special nozzle that adds the material, that adds metal powder, for example, in the special area that we need. So we can create any diameter, or we can create yes, bigger size using this technology, but again, it's a part of additive manufacturing. So what about disadvantages you think more? Maybe about cooling channels, what do you think about the channels? The size of the channel, the size of the holes?
I mean, what came to my mind still is, I think the 3D printing can be a little bit tricky for some shapes. Like, for example, shapes that are completely horizontal need these support structures, I think. And I mean, they have to be kind of milled off afterwards, and maybe that's a bit difficult for some parts.
Yes, exactly, you are right. We have this kind of operation as post-processing. We can use chemical polishing by using some liquid chemical compounds to clean out all these cooling channels, because during the 3D printing, inside the cooling channels, if you will not build some support material for these cooling channels, there will be some suspended, not melted material, for example, metal powder. It's a small kind of particles that will be blocked this channel, and the fuel will not go directly in usefully by using this cooling channel. So this cooling channel should be cleaned by special methods. Yes, this kind of disadvantages. In advantages, the time of the printing, it takes less. It depends of the again geometry. As I told you before, we can make complex shape with as one complex form. We can join all these components together to make one complex form. This is advantage. Advantage about some materials. Yes, you're right that we can not use all materials rather than in, for example, casting. But here we can make some compounds of, for example, metal powder. For 3D printing, it's called another part of another kind of additive manufacturing called SLM, selective laser melting. The materials that used, it's metal powders, compound of chrome nickel. It can be used titanium to make your construction lighter. So there, some disadvantage again to find out correct smooth of laser power to melt exactly material that we need. But if we choose, if we made some parts of experiments, we choose the best parameters for the laser, we can use any material to create our complex form, complex shape for these rocket engines. Is in advantages that we can create these components fast. For example, in traditional casting, first we have to make cast form or mold form, we can call it. We are using CNC machines first to cut out the contour of our combustion chamber for the molding form. It took from 1 week to 1 month. In 3D printing, exactly, you have your 3D model that you want to fabricate, and you are just load it in your 3D printer in SLM machines, for example, and you can create this kind of the parts. This is advantages. Time, uses of material, and we can create complex shape, and can also create the detail as one part, joining together some components. Here you see an experiment that NASA made after the printing of this nozzle for combustion chamber. You see that the holes are great, have a correct geometry for the fuel injection. As a result, you see on the screen the fluid dynamics goes directly in useful form. And also burning experiments. One engine in different sites, it's took from 400 Newton thrust to 150 kilonewton. You see how power this rocket engine. Again, they made this experiment with 3D printing fuel injectors. They printed injectors, but I think the combustion chamber was made by traditional technology. I know in some papers they are writing that they are printed just these injectors. Others says that some part of the combustion chamber was made by this 3D printing, but we are don't know exactly. But they say nowadays they are making totally all the engine using the. And about the big size that you was talking, this is a direct metal deposition technology. As you see, there is special nozzle that directly throws the material. Here it's metal powder in all the area that, and we can create a bigger diameter. For example, from 20 centimeters, it can be diameter to 1 meter, because the arm, we call it robotic arm that moves in direction and puts the material in that region that we need, and we can again layer by layer create, for example, nozzle for the rocket engine. And you see at the right screen the surface of that nozzle, it's more smoother. I think after that they're used post-processing called using by CNC machines. And after that, the detail was created by 3D. From the left side, you see the a little bit roughness of the surface after the 3D printing, but they created small cooling channels for the fuel that will cool the whole construction. Another liquid rocket engine made by Additive Manufacturing. I think it's a Rocket Lab, Firefly company. I don't know exactly. They made complex rocket engine. Even they printed some pump details, some pipes using this technology, because the geometry was complex. That's why they thought that it will be useful to use 3D printing. Here's some characteristics for that small rocket engine. It takes about 24 kilonewton of thrust. Burning time 150 seconds. That's good enough for this kind of rocket engines. The diameter 350 millimeters. I think it's talking about the nozzle. Manufacturing process is electron beam manufacturing. It's a type of the selective laser melting, kind of additive manufacturing or 3D printing technology. Components that made by additive manufacturing, it's combustion chamber here, injectors, pumps, as I told before, some main valves and propellants, and also some pipes was made by this technology. I think it's for directional control of for the satellites, I think, or for the some spacecrafts. I don't know exactly, but the rocket engine made by additive manufacturing.
Sorry,
3D printing.
may
Yes.
I ask, would you
Yes,
please
of
go
course.
back one slide? Huh?
Uh-huh.
Can you explain to us what is burning time?
Again?
What is burning time?
Burning time, it's time that this rocket engine it works. It took about 150 seconds to send, for example, aircraft to the air. It's, I think, second stage for the satellite, second stage for the aircrafts. That's why it's small, these rockets. Burning time, it's a I think we can call it working time of the rocket engine.
Okay, so it's only used in 150 seconds. It's only used in about 2 minutes, right?
About 2 minutes, yes. To send, I think, satellite, it's second or third stage of the whole rocket. That's why it's so small this time it takes. Just to send the satellite, for example, to the orbit. That's why it's not needed. Yeah, too much time.
Thanks a lot.
Now in International Space Station, they tried to make an experiment in anti-gravity. We can call it in small 3D printers that worked in anti-gravity period. I think in Japanese scientists, they made some parts using FDM plastic or some ceramic materials in International Space Station. They printed 14 objects, including some ranges and sent them back to the Earth to test the characteristics of the material. How does it work in the Earth? Because as you see in International Space Station, there is no gravity. That's why this experiment was difficult enough to make it. Also, material, I think, was used in 3D printing. It's was some types of metal powder. I think they magnetized it to put on the surface of the platform, and after that melted by the laser source of energy. They create, but most it's useful in space. I think the technology that prints by the plastic. So the plastic models, it's more useful to print in International Space Station. And again, it's a fast way to print something, for example, broken parts. It's useful. If you have your 3D model, you can create in a few minutes or hours your detail to change it. What do you think about the 3D printing in space? Is it useful or not, especially in International Space Station?
Yes, I think it's very useful because if there is any damaged part, they can make it automatically there, so they don't need to go back to Earth to reproduce some parts. Yes.
What else? But there's small disadvantage. What do you think? Which one?
Okay, there is no gravitational, so I think it's hard for the machine to make
Yes,
the
and
component.
the most important disadvantage, what do you think?
Oh, I have no idea, sorry.
It's a material. Always we have to send to International Space Station plastic material, powder, metal powder material. This is maybe one kind of disadvantages. Yes, we have the machine 3D printer, but how we can create our detail without material? That's one of the disadvantage of this technology. But in another side, yes, it's very fast way to create your detail using this technology. And the most advanced projects for the future, as you see, or even this billionaire Elon Musk says that he wants to create own colony on the Mars. Using this technology, we can create some buildings. This technology is useful to create some blocks, and we can melt them using the source of energy laser, and the energy we can take directly from the sun, because there is no atmosphere on the moon, for example, or on the Mars. It's very useful to absorb energy by sun panels, to use this energy to transfer to the laser energy and melt the material of the Mars or of that planet that will be sent our 3D printer. In NASA or in some universities, they made an experiment. Have you heard the experiment about lunar regolith, lunar material? That Apollo mission sent to the Earth this kind, some materials from the moon, and they tried to melt it using laser source. The material in composition of elements, it was very familiar and similar with our Earth rock material, kind of the ceramic material. But there was some, they also used some glue material to join together these small particles of the lunar regolith. But in 80%, this material is similar to the rock on the Earth, from the mountain rock of our Earth material. That's why this is one of the idea to do not send our, for example, metal frames or metal construction to the other planets. We can create like external parts of the building using the same material that on the planet. Just make some blocks, melt them to make some blocks, and from these blocks we can create an example of this kind of maybe buildings. And after that, we can send by the rockets some frames to make construction stronger. That's why. But the idea to create some buildings, some plants maybe from the materials that exactly on that Earth. What do you think, guys, about? Is it useful to send one machine that will create the blocks from the material that on that planet?
I think it's like this a similar advantage to having a 3D printer on the space station, right? At places where it's very difficult to get new materials from Earth to these places, it's very good if you can manufacture them right there. So yeah, I guess it's very advantageous, right?
Yeah.
I have a question.
First, yes.
Okay, sorry. I have a question. Why until now we are not still we've not yet see any kind of machine in the world. For instance, maybe with this machine we can create a home from a rock, for example, but we never see this machine exist.
I think the most excuse because it's very expensive to send this kind of technology. But no, the missions were sent to that planets first to see which compounds that planets have. Are they similar to other Earth? Maybe even if we'll send the laser power to that planets, is it possible that it will melt that material? Maybe it's stronger, maybe not. We have to choose special modes for the laser, for example, or for another kind of technology. We don't know the chemical composition of that material, and again, different gravitation. Some reasons do not do that kind of mission, because we are thinking on the Earth. Yes, we'll send this apparatus, but how does it work on that in that conditions? Maybe not enough researchers in this area. That's why we still don't have this kind of missions. That's why we didn't send the machine that were built buildings maybe even on the moon, the nearest planet to the Earth. What else? 3D printing for space. These machines also used to print some satellites compounds. Have you heard about Cube satellite? It's a mini 3D printed satellite that frames were printed from the plastic FDM technology. They were sent to the orbit. Many of these experimental satellites, again using 3D printing. The compounds, the materials that was used, it's advanced chemical change to plastic for the special conditions of the space, because as you know, it's very cold out of the Earth, and there's no atmosphere there. That's why it was special plastic and a special 3D printer that printed these small cube satellites. In a European agency, they also said bigger. It was 2 meter by 1 meter satellite, whole satellite. Some panels, I mean the frame for the panels was printed by the 3D printer, but using selective laser melting technology. It was printed from the metal. From the left screen, you see the advantage rocket engine, but the company it's used, I think it's United States or German company, and I don't know exactly. They used the selective laser melting technology to create this rocket. See you in space. You know, when we will finish our lesson, I will give you some small homework. It will be your task for the next lesson. And in the next lesson, I will try to show you our lab of additive manufacturing in our university, which kind of the researches we are making here, and which kind of technologies we are using. We have 3D printer that using metal powder, and we are printing some advanced details for the aircraft engine, but mostly for the jet engines. Here I would like to show you some videos. And an example of 3D printing. Is it visible to you?
You know, metal additive manufacturing, it's an amazing technology which has tremendous future applications for manufacturing. But if there's ever been one knock about it, it's that you can't make large parts. Now I'm with James Hockey, he's Director of Business Development for Incodema. And Jim, we're standing next to a monster of a metal additive manufactured part. Now you built this, tell me how.
Yes, well, we used the EOS M400 machine, single.
You see, guys, this is a 3D printer that I was talking before, EOS machine. It's the technology is selective laser melting, and the laser powers and source energy sources.
Laser. It's a 16 by 16 by 16 inch build platform, and we used this part here and designed it and stretched it out so that we could maximize that build platform and show exactly how large a part you can actually build in this. So this is aluminum. This part probably weighs about the 12 to 13 pound area after being built. Very lightweight and solid, fully dense off the plate, but.
Okay, guys, who will tell me what is the disadvantage of this technology? What about the roughness of the surface? Is it good enough?
Yeah, I mean, probably if there's some gas flow through it, it will get turbulent and all these things, I guess.
Yeah, that's why you see there's some roughness.
As you can see inside, it is hollow.
Now, it's historically thought of as an expensive way to make things because you're using expensive raw material to begin with and an expensive process at the same time. But obviously, if you're lightweight, you're also using less material at the same time. So, how much of that cost can you win back? Is the cost in time to market? Is in lightweighting? Is it using less material?
Cost is in the build hours. I mean, the layer process, the Z, kind of drives the pricing. But again, you're building near net shape, so you're not using as much material. You're not buying a block of Inconel or a block of titanium and machining down and wasting a bunch of material. So you're doing finished machining, fine-tuned machining. Very little parts or very little material is wasted.
Now, do your customers, do they optimize the design for additive, or are they bringing you parts which are originally designed for subtractive and saying, please 3D print this?
In a lot of ways, they're bringing us parts that are already being designed for conventional. They are now redesigning parts for additive, so that they are building parts.
You see, guys, here before printing, they're using some calculations.
Of the structure.
In ANSYS, maybe you heard this kind of
are now redesigning parts
for fluid
additive.
dynamics. You see the cooling channels that exactly was created, was developed exactly for this technology, because these technologies makes possible to create this kind of difficult geometry cooling channels. But before, we always have to make some calculations.
So that they are building parts with things of the structure where you're changing the whole shape, so that you can build these parts in the layer process as opposed to trying to do any secondaries afterwards.
Now, this is aluminum. What sorts of materials typically do you work with at Inconel?
Inconel, stainless steel, titanium, cobalt chrome, Hastelloy, many different materials.
Okay, and those materials you described, some are refractory. You mentioned some super alloys in there. You also mentioned some products, I think, of some medical applications, for example. But is aerospace, would that be a major market?
Aerospace is our major market. Yeah, we are 95% aerospace focused.
Now, it's in aerospace, of course, it's engines in particular, expensive. The hot section is really expensive. A lot of investment casting, a lot of tricky stuff, and then you do a lot of post machining at the same time. Is this technology going to work its way into the hot section? Are we going to see, fully dense sort of Inconel turbine blades on a mass production basis?
We are, and they are there. So we are doing parts right now where we actually have parts test fired by NASA, test fired by companies like Aerojet. With the technology using the alloys that you discussed, but aerospace is grabbing this because it is difficult to make a lot of these parts in casting or anything that's an assembly. So once they get into multiple pieces and they're doing raised welding, ultrasonic welding, they want to avoid that and get away from that, redesign and use additive so they can build these parts wholly, holistically in one piece.
Now, in terms of surface finish, historically, we're used to, when you get to very large 3D printed parts, giving away something in terms of surface finish. But this surface is actually very uniform all the way across. So I'm a little surprised to see that. Is this the future? Are we looking at finer and finer surface finish?
You will be looking at finer and finer surface finishes. So the process of the melt pool, the material itself, the different granule size that we get in, and the amount of power we put into the build, into the layers, will change that size and the resolution.
Large, precise, and accurate parts with a good surface finish, says James Hockey from Inconel.
So you see, guys, here that gentleman said that they are using this technology to create complex shape form. Some disadvantages have because of roughness of the surface. Again, which kind of Who remembers which kind of materials they are used? I mean, metal powder.
I think this part he said was aluminum, right?
Yes. And what else? When the interviewer was asking which kind of materials you are using, what he said about it? Don't you remember?
I think he said, like he said, yeah, several different materials. I think some nickel alloys, like this. I don't remember the name, but this
Stainless steel,
Yes, titanium. What else?
ceramics.
I think he said Inconel as well, like these special alloys.
And you remember he asked why some details, for example, for the jet engine, are not made by traditional technologies. What he answered? Don't you remember? He was asking about the molding, about the casting. There was some tricky thing.
If I haven't wrong heard, because there are a lot of very hard shape,
What? Yes. What else?
complicated.
Yes, and he said, if you remember, it's takes too much time to make the molding, the casting form. That's why it's better to print it in the 3D printer. And you saw the process, how it occurs. Each layer firstly puts on the surface of the metal platform the small, tiny level of that powder, metal powder. And from the top, it melts using by the laser. Each section was melted layer by layer. And then our platform goes down. I'll say it's from 30 to 50 micrometers. It takes each layer, and after that, the process is secure till the detail will be finished. What else? Let me show you another short video. I used the large scale parts. Example of Here's technology called direct metal deposition. You see the big roboted arm that puts exactly the metal powder on the special surface that we need, and we can create large-sized objects. This is special nozzle. You see the source of energy goes directly that direction, and from the left and right side, send the metal powder. Amazing, isn't it? So do you have the question from till this moment about the additive manufacturing? And I have another small presentation if you would like to hear about it. It's exactly about 3D printing, about the SLM technology. Okay. Now I will try to talk about our research of our university, what we are making here, and which kind of technology we are using. Here, additive manufacturing technology. As I told you before, it's a process of joining 3D metal or any kind of the material layer by layer and manufacture very complex shape. Here is an example of gas turbine engine and some fine metal parts designed by Grossman factory. So first it starts from vocabulary, additive technology. This vocabulary comes from the university, if you heard, it's MIT University, because they were first guys thought and who had an idea how to use the source of energy called laser power and how to join the material, especially metal powder, and which kind of the source to use and how to compound these two technologies to create new parts. That's why they put that like a vocabulary that additive technology is a process of joint material to make objects from 3D. So which kind of additive manufacturing have here? It's additive layer manufacturing using a source of energy laser. You see a laser metal deposition, short LMD, direct energy deposition, DMD, powder fusion. Powder, most of all, they are used metal powder. Selective laser melting, this technology we are using in our university. Direct metal laser deposition, and also electric beam melting. So what we have to know for our additive manufacturing technology, we have to create our 3D model, and yeah, 3D model we can make in different kind of programs. It can be SolidWorks and NX. Yes, and I have a question. Which kind of the programs are you using in your university? Are you modeling or do you making some models or maybe some schemes?
Yes. Yes.
Which kind of program you're using?
In my university, we are using NX Siemens.
Siemens NX, yes, okay. What about the others?
I used AutoCAD and Autodesk Inventor.
Great. What about
Creo?
It's for 3D modeling or just to make some shape or some movement calculations?
3D modeling.
Okay, and after that, and I was asking before this question, have you got 3D printers in your university? No, yes. Okay. But I think you heard that after that, when you created your 3D model for the 3D printer, it's the best format is STL, in short for stereolithography. I mean, when you're creating your file, it should be .stl. This is a special format for 3D printers, even for FDM4 plastic printers, even for SLM printers that using metal and laser source. Here, after that, we also need material, but here we're using in our university metal powder and 3D printer, the equipment, the machine that will create your detail. And after that, you got your detail. So application of additive technology you heard before. I was talking about aerospace segment, but also we can use 3D printing for molding. You see, with the complex cooling channels, we can print some small size casting mold form. In medicine, as I don't know, you heard about the news last year, 2020, it was very difficult to us because of the pandemic, because COVID infection. In Italy, two guys printed a special pulp for artificial lung system for that apparatus, small pumps using this 3D printing. In medicine, we can print some bone parts for the skulls, for the breaking boards or bonds. But first we are making tomography to see the shape, and or we can making 3D scanning for the broken bone. And after that, to load this model and again work with it to change. We can say broken part, broken. In automobile, the super cars as a Bugatti, they're printed brake system from the titanium. They used SLM technology. You see, it's not just very advanced for aircraft segment, but also in many kind of manufacturing, we can use this kind of technology. And the process, how it occurs. The powder bed manufacturing cycle. On the bed platform, as I told you before, we put small, tiny level of the metal powder, and after that, by the special trajectory, laser melts and creates our future model. It's called fabrication modeling. And yes, another question to you. Let's think about it. Which explanation is better for 3D printing? Because I don't know, 3D printing, in my opinion, you're printing some on 2D on the paper. We can call it manufacturing. We can all call it fabricating. Some people say it is growing, but growing it's more for the nature things. What do you think? Which word, maybe which explanation is better for 3D manufacturing or 3D printing? What do you think, in your opinion? Sometimes we are manufacturer, sometimes we are fabricating. Some people call it more 3D fabrication, 3D manufacturing. In your opinion, which one is better? Or let's talk that it's 3D printing, it's better.
Yeah, I think maybe manufacturing is better because it more emphasizes this aspect of creating something from nothing, kind of like, I don't know, for me it sounds fabrication is more like you have a part and you change it a little bit, but 3D printing is more like you have nothing and then you manufacture something out of nothing.
But you have 3D model. We cannot say that you don't have nothing. Yes, and you know, to print something, there is some disadvantages. I will talk later. Somehow you have to change even your 3D geometry exactly for the 3D printing, to change some holes, to change even geometry, to achieve more better construction. I will show you how. So, and this is equipment that we have in our university. It's German machine called SLM 280. The numbers on this machine, it's the size of the build platform, the maximum size that we can create using this equipment. 280, it means the width and the length size is 280 millimeters. And the maximum height that we can build up, it's about 350 millimeters. So the more some parts that it consists of three main blocks: operating system, or we can call it laser unit, the printer controller, the computer, the brain of the machine. We can build chamber where the process occurs. Here you see inside the chamber, it's a build platform and the detail on the surface of the platform. And a powder sieving station. The plus of this technology, the powder that we are not using during the printing, we can sieve it and use it again. So there is no some extra, bad material like in CNC or in cutting. There are no the extra material that we are throwing out. We can renew and we can reuse this powder. That's why it's plus for this technology. We are not throwing some extra material. Some features for the 3D printing. You see there is formula that we are using to find out the best parameters for laser power. So source power, it's a laser. And to find out the best parameters, we are using this formula where the P is a laser power in watt, V it's a scanning speed, the speed with and that the laser moves on the trajectory. H it's a height distance, the distance between melted tracks of our laser power. And also T it's a thickness of the layer, and amount it's equal to energy density, how much energy we need for our from each material. For aluminum, it's for example 50 joule per millimeter cube. For titanium, it should be greater, melt it up. And also we have to find out the balance between these parameters, because if we put too much energy, even we can, I don't know, maybe evaporate this material, so it will not even melt on the plate. So the process that metal powder it secures its absorption of the energy. It can reflect some percent of energy and scattering. And the particle, the size of the particle, it's varying between 30 micrometers to 50 micrometers. It's about 0 each particle, metal particle. If you look at the, for example, if you look in a microscope, you'll see very small, tiny spherical particle of the metal. The process to create this powder, it's somehow difficult. It can be atomization. It can be very fast compression. In the factories on the plants, you got about the ton of the melted metal, for example. Let's talk about the aluminum, and it throws from the special, very tiny nozzle at a very high speed, and it can create this small spherical particle of that metal. It's called extrusion or atomization. This is the technology how to create this powder metal for the 3D printer. So which kind of experiments we are using, we are making in our lab? First, we have to know, is this metal powder is good enough for our equipment? We look at a special electric micros analysis we making, you see on the right screen. This is the small particles. Some particles are circular around. You see there's some cracks even on the surface of each particle can be some cracks. Later it will make some bad effects for our future detail. That's why we have to find out the best ones. And again, elemental composition of the, here for example, heat resistant steel, which kind of the compounds it consists, because it's important to find out the mood, I mean the parameters of the laser for each compound of the metal. So everything it starts from this microspheric analysis of the metal powder. After that, we are not starting with our whole detail. First, we have to print some samples. You see here, it's small, this samples. It's about 5 millimeter sized. It's made from heat-resistant steel, and we create about 27 samples. Do you have any idea why we are making these samples? Okay, we are making to find out the best parameters for moves. As I showed you before, this formula, the power of the energy, the scanning speed, the height distance, and thickness layer. So for each sample, there is different power. For example, 3 samples, we are making with 300 watt power. Another 3 with 310. So, and the difference, it's about 10% to create the best one. For example, these 3 samples have the same power, but different hatch distance. Different hatch distance, but the same power. Different thickness of the layer, but the same scanning speed. And after that, that's why it takes about 27 samples. If you multiply 3 samples by 3 modes, and again multiply by 3, it's got about 27 samples. Totally, it's 9 samples with 3 different. And after that, we make some mechanical sample experiments. We shrink these samples, we expand them, we rotate them to see how they're strong enough. It's called this mechanical experiment or mechanical analysis. After that, we are cutting small sample section. After the shrinking or expanding, we somehow polishing them to see the inner structure. Does they have some holes maybe inside the structure? Does this structure is good enough? You see on the right side of the screen, there's small, some tiny. We can see, is it good enough? Which mode is better? And again, elemental analysis of steel. So this is in percent mass value of compound of this sample. It have oxygen, it have chromium, molybdenum, ferrum. It's see them most. It's consist ferrum element, and again some nickel and molybdenum compound. After that, when we made an experiment, we choose the best parameters. We can create our part. Here it's a section of blade turbine jet engine nozzle. We changed some geometry, for example, deflector and the blade. The cooling channel, we changed the geometry of them. Why we did it? Because during the process of manufacturing, our program for 3D printing automatically builds up some support materials. It's needed to support our structure because, as you know, our detail growing or manufacturing through this process, and we need some suspended or inclined surfaces support them with a special structure. These support materials are made from the same material as our future details. So we optimized a 3D model of the nozzle. We put inside here, if it's visible to you, small cell block. The section of the small cooling tiny channels also changed, and deflector was put inside the turbine blade. In traditional technology, it's take too much time, and it's hard to create this blade. Why? Because first, using the molding technology, you are making the shape of the blade, and after that, separating, you have to make this part called deflector with a small cooling channels, and after that, you are put inside this blade. But here, we made it like a complex one single form using 3D printing. Here is a technological process of preparation. First, you see, we have on the program virtual build platform. Here, with green color, we put our future detail. It's a section of the blade from the titanium, and after that, automatically this program generated supported material. You see it's on the right screen with the red color. After that, it can be easily take it out. But before the printing process, we are here making some simulation of this 3D printing. You see the temperature comes from the downside to the up. At the top, there is cold enough because it's comes to the end of the process. But most energy starts in the beginning, when the first layer it starts melts, and our laser power energy sends much more energy to that region to create the first layer of our blade. And after that, layer by layer, we achieve our detail. And on the left side, you see the result of our blade gas turbine engine nozzle with the 3 blades, with the difficult geometry deflector inside. What else we made using this technology? It's a combustion chamber for the jet engine. This experiment we made in 2015, I remember. It was one of the PhD work. We created this combustion chamber for the real engine. We tested it. You see here some bench tests. So it took about 8 hours, and after 8 hours, it doesn't change its shape. So the complexity and the strongest of this combustion chamber show that this technology, selective laser method, it's useful to create such details as the combustion chamber. And as a result, after all these kind of experiments in additive technology, we found out the best parameters for the laser source. We changing a little with geometry to print it. We are creating some special support materials to make it more functionality, to support our structure, and after that to easily cut out from our build platform without any difficulties. And it's again, we can create a short product cycle time with complex part, join it together 3 or 4 compounds and melt it as one complex shape, complex shape, for example, blade, in this exactly experiment. So this is how it does work, selective laser melt. So do you have questions, guys, exactly for this, to this moment? Okay, I have questions to you. Using this technology, is it possible to create, for example, aluminum detail, but without to making an experiment with the samples? Is it possible to create exactly the model without the process of finding out the parameters for the laser power? Using internet source, for example, to read some research papers. For example, one scientist made with that exactly parameters that he used, and we are just using the same parameters. Is it possible to create complex shape from aluminum, for example, without an experiment?
I think maybe the surface properties do depend like on the geometry of the part. So I guess you would have to test kind of for each individual part, maybe.
And what about the parameters? Maybe that parameters in the research paper was totally different, or another kind of the materials. Okay, he says, or he wrote that he used again the same material, aluminum powder, metal powder, but where's the guarantee that chemical composition is the same? That's why we have to always make an experiment. Okay, any questions? No? Yeah.
Yeah, maybe I think I remember it was a long time ago, but in the little 3D printer we had at the university, it was always kind of, I mean, it could make the parts either very, very good, very smooth, but then it would take extremely long, or it would make it coarsely, kind of very rough, but quickly. Is that still the case, that you have to kind of do this trade-off between speed and quality, kind of?
Yeah, we have again to find out the balance between the quality and the speed of this printing. Here, yes, we before to put on the product, on the manufacturing, the detail, we have to make, after the samples, we have to create experimental model, because to see the characteristic of this first detail, we can call it experimental one. Do not say, oh yes, it was good enough on the samples, but it doesn't 100% make you believe that future details will have the same characteristics. That's why, yeah, you're right. First, we have to print an experiment detail and to test it. For example, as we made with the combustion chamber. Any idea, guys, about the medical usage of this technology? How it can be useful in medicine nowadays?
Yeah, I mean, we already saw this picture of some part of a bone being made. I guess in medicine, to replace human parts, they are very individual. And so it's probably a lot of work to cast molds or anything with a different process. So 3D printing is kind of useful because you just have to kind of scan the patient, make a 3D model, and then you can immediately produce the part without, yeah, creating additional molds or things like that, like for bones or joints or teeth maybe, or these things.
Yeah, but you know, for medicine, there are special materials. For example, titanium powder. We cannot use the same like in traditional manufacturing, because you put inside the organism. We don't know how it will react with the organism. Maybe it will be not good enough. Maybe in medicine, you know, when even they're choosing the material to create future bones, broken bones, for example, they making kind of research which kind of chemical compound that this material do not to make it stronger. First, anti-corrosion, because you put it inside the organism, to see even for the most or for laser power. It should be strong enough. It should be more poison, we can say, for the organism. That's why it's useful to create very fast, very complex shape, but if you look from the poisonous for the organism, it will be somehow a very difficult question. Is it useful, this technology, or not? But for the other ones, yes. Maybe for exoskeleton, it's useful when you are not putting inside the organism, just to make like helper for the lifter. Like, I don't know, even we can make Iron Man suit, something like this. Yeah, but for something external, but not to use them for internal. Okay. It was very interesting, I think, for you, these lectures. You found it interesting for this process. Let me give you some small homework, home task. You see the chat of our Zoom. I'll send the link to you. From this link, you have to download a special program. It's called Autodesk Fusion. I heard that some of you used Autodesk programs for the modeling, for the other, this kind of 3D modeling. In this program, you have to make topological optimized design. I will show you a short video how to make it, but first I will send you a link. You got it? This is official site for Autodesk Inventor. And the program that you have to download, it's called Fusion 360 NetFab. This is the program. And now let me demonstrate what exactly you have to do. There's short videos.
World of Fusion 360. In this video, we'll explore a little about generative design in Fusion 360. Not a little.
You have to make some generative design. You can
now,
change any structure that you want, or maybe even you have your own.
We're going to generate design for brake pedal. Without further ado, let's get started. So, here we are. Before switching to generative workspace, we may have to focus on two areas. One at the pivot, based on which pedal rotates, and the area at which we apply force. These are the main areas which we have to focus, and the rest is for reference only. Let's look at the properties for this pedal. The mass of this pedal is 229 grams approximately. The material is steel by default, but we are going to manufacture it with titanium. Let's go and change the physical material for this pedal, though it doesn't affect the generative design. In metal, scroll down. And select titanium. Now switch to generative design. Let's have a look at from the top. You can learn all about generative design by clicking on Toggle Learning panel if you want. And study, we have new generative study, but we have one already here by default. Coming to study settings, what we want to focus is here actually increase the resolution. For better results, just a bit and click OK. Moving forward, click on Edit Model. Under Model Components, inside Bodies, we are having only one. For generative study, we must have more than one body. That is for prisms and obstacles. Create a sketch on the pedal face and select the face. Then press P to project the face. Finish the sketch and select the sketch to extrude. Select the opposite face as distance. Change the operation to new body. Let's create another sketch on this face and project the circle again by pressing P. Perfect. Observe the circle 2 mm inside and finish the sketch. Select the profile, not inside, and extrude the other side. Change the operation to new body and click OK. Now we have to tell the software that not to fill the material where we don't want, particularly at the connectors such as bolts and nuts. For this model, a bolt will be at the pivot. Click on Connector Obstacle and select the inside edge. You'll observe that a shaft through hole is passing to the other side. Just by adjusting the parameters inside the dialog box, you can get our connector. If you observe here, it had created a shaft diameter as 12 mm. I want to change it to 11.85 mm. Now, click on bolt head. Enable bolt head on both sides after the shaft length from 24 to 4 mm. Similarly, head length as 10 mm. Let's go ahead and finish the edit model. Select preserve in here and choose the geometry that we must need. Select the pivot and the body on which force acts. We have already selected obstacles. Then we have created a connected obstacle. Coming to the structural constraints, let's hide the obstacle geometry so that we can see pivot. Face to be fixed. In practical world, we apply force on the pedal and the pivot rotates only in one axis. Remaining two are fixed. This is only for some extent because of the spring. At extreme point, it won't rotate. We are considering that extreme point and fixing this face in all directions. Apply force on the face. And let the amount of force be 2000 newtons. Here comes objectives for our requirement. We can choose minimize mass or maximize stiffness by varying limits such as safety factor and mass factor. For now, I'm going with minimize mass. Coming to manufacturing. Unrestricted will allow the machine to generate an organic design. With additive, we can 3D print the part by overhang angle and minimum thickness parameters as base. In milling, we have 3 axis, 2.5 axis, and even 5 axis. This design is not supported from 2.5 axis machining. Let's add 5 axis machining by clicking plus sign in here. In 3 axis, switch the tool direction to Y positive and click OK. Choose the material for steady. We have many materials in here. I'm adding titanium and Inconel 625. Oh, we got a warning here. It's telling that the head diameter is large. This is because the model is inclined. Let's go back to the design workspace and rotate the model to fix it. Select body and press M for move and rotate. Let's rotate this body to 45 degrees and switch back to generative workspace. Now observe that everything seems perfect. Holding the gravity about 90 degrees by changing the direction type. Let's have a preview. The preview is not what I want actually. I want material to be added in this direction. Let's go back and edit the model. And in combine, change operation to cut. Select the main body as target, pivot and pedal as tool bodies. Check the keep tools and click OK. Edit the starting shape and select the main body. This warning is because we've added the bodies in design workspace. There is no problem with that, but I want to view them back now. Generate the design. It takes some time to generate output. We'll explore the generated results in the next video. Click on the link in the description to watch it, or from the info in here. Hope I'll catch you in the next video. Thank you for watching.
So you got it a little bit. I'll try to send this video also, how to make their model. And also they have, yes, it's already sent it. break output the model for that program. You see which kind of the calculation he did. Firstly, the movement of this part, how it will be situated, the fixed point, where that pedal will move, in which kind of directions. He chooses the direction. He chooses the force that will be used. So you got the model in the chat. Is it visible to you? It's called break output version 1.3 F3D. And now I'm sending the video. So do you have any questions till this moment? I have a question to you. What is the generative design in your opinion?
What is what? Sorry, I didn't.
Generative design that we watched the video right now. Generative design for the parts, for the models. What does it mean?
I think it means to make the part in a way so that it can be easily printed, right?
Somehow yes, but not exactly. Generative and design. So you're making, you're changing the design. It means it's kind of the optimization. We can call it topological optimization. So what does it mean? When you have your object, and as you remember from the video, he chose the main points where the force will be applied and where this whole the model will be completed. This is the important points where our virtual model will not be moved, will not be shrinked. That there's the standard dimension, and between this point, it can be any kind of structure, and the structure can be changed generatively. So it can be solid, like solid metal pedal, or it can be just striped, some tiny things, but the construction will have the same strongness. That's why it's called some topological optimization. We are not changing the size of our whole model. We just have the points that will not be changed, the points where the force and all these conditions will be applied on that model, but the distance between that can be changed. The structure can be changed, the geometry even can be changed. It's called as a generative design. Generative design used in medicine, for example. It's used in aircraft industry. In aircraft, in generative design, we cannot change our combustion chamber, but we can change some maybe piston or holder of that engine. We can change it there. So in medicine, there are too much generative design because the shape of the bones are irregular, and it can be changed. Short question to you: did you get my videos in the chat and the model? Okay, got. It will be homework to the third lesson. As I see, it will be third lesson and the last one, and we will check it out, your homework. You can first create your own model, or you can use this 3D model and to make the same generative design for exactly this model. But as like let's say maybe kind of present from us, you can send us by the mail your model, and we will try to print it on the 3D print. It will be very great, and send it to you by the by the mail. I hope it will be possible. On the next lesson, we will show you our we will show you what we are kind of experimenting. It will be somehow virtual excursion, and you'll see what we are making. So, any more questions for today's lesson? So maybe you found it interesting to you.
Yes, I have a question.
Yes, okay.
When is the deadline for our homework?
The last lesson, the third one. I don't know exactly your timetable. The second lesson will be in our lab. The third one also, where it's called Professor Victoria Kokorev, maybe the who is reading the lecture, and it's called 3D generative design or something design. I don't know. I think it's 29th of July, something like that. Yeah. And I have a kind of excuse for you. Sorry for my level of English. Maybe it's not good enough to send your whole information during my
No,
lecture.
your English is really good. It was absolutely no problem. Yeah.
Really, maybe I didn't explain something very important moments during my lecture. Maybe I have some mistakes.
Nah.
Sorry for that.
I didn't notice any problems. I think it was really good. Yeah.
Thank you.
Yes, for me, you are speaking English very good. It's no problem as long the other one still understand you.
Thank you. Thank you. Thank you for that. As you see, totally conclusion for our lesson that this kind of technology has, as all the technology, some advantages and disadvantages. Advantages maybe in speed, in the usage of the materials, in the complexity of the shape, the plus that we can create any complex shape. But disadvantages with some special moments, I mean, in creation of cooling channels, the difficulty that for not all the materials have the standard parameter of laser melting power. That's why always when we achieve new material, we have to make an experiment to choose the best parameters for the melting. And again, experiment for the model, not just exactly making all the next models using just the same parameters, because first we have to make experimental one. The first one to make an experiment, burning experiment, some mechanical testing for that model. And after that, we can create all the models for the engine, for example, or for the medicine implants. For the advantages in additive manufacturing, the one kind, it was direct metal deposition, where the robot arm was sending the material. With help of this technology, we can create bigger details with bigger shape size details. For example, the big nozzle for the rocket engine for the first stage, not just for the second or third one or for an aircraft, but for the first stage. For the satellites, it's very good technology that we, in short time, we can create such small satellite frames for them to put inside the electronics. Useful. This is useful technology for that. And in the future, it's like a variant, one technology to create future houses or homes or plants on the another planets. But we have to think about the material that is situated exactly on that planet. Again, some conditions for the gravity, again, it can be different. For the conditions, even our equipment will work on that planet. For example, yes, we created a printer, but will it work on the moon? We didn't make this experiment till now. Will it work on the other planets? We have to think about. And in another side, this technology is, I will not say perfect, but good enough to create to manufacture our goods, our things for our daily life, for aircraft, for medicine, and all that kind of segment. So something like this. So guys, again, I would like to say thank you for this lesson. I hope you found it interesting. So if you don't have any question, I would like to say goodbye to you and see you next lesson. So no question, guys? So, okay, thank you for this lesson and see you next lesson. Bye.
Yeah, thank you too. It was a lot of fun. See you next time. Bye-bye.
See you next time.